Hello guys, we're going to be looking at constructing a few proofs using the compound angle formula. And as you can see here, we have our first question, which is question A. Now, the first step one, is to decide which side I'm going to take, right? And once I've decided that, I'm going to have to write a statement. So looking at this, we could probably go with the left-hand side. So I'm going to write a statement that says taking the left-hand side, which we're going to abbreviate LHS, all right? So I'm gonna take that left hand side, and when I'm finished, it should look like the right hand side. So let's go right ahead. So this is saying that the sine of A plus B over cos A cosine B, when I break this down, it should actually look like the right hand side. Now let us see if we recognize anything here. And bear in mind that the right hand side is tan A plus tan B. Alright, looking at the numerator here, we know that we can apply the compound angle formula here for sine. Now we can go ahead and say recall that sine of A plus B is equal to sine A cosine B plus sine B cosine A, right? And there are several manipulations. It doesn't really matter because multiplication is commutative. So what it means now is that I'm going to go to the numerator and I'm going to replace that sine A plus B. So this actually becomes sine A cosine B plus sine B cosine A all over the cosine of A cosine of B. Now, to construct most of our proofs, it requires you to understand algebra, right? So basic algebraic skills. So at this point, what I'm sure that I can do is that I can split the numerator with the denominator. So I can actually go ahead and write this as the sine of A, the cosine of B, all over the cosine of A, the cosine of B, plus the sine of B, the cosine of A, over the same denominator, which is cosine A cosine B. Alright, let me just scroll this a bit now. Alright, so what do I do here? I can actually reduce this. If we notice in the numerator here, we have cosine B, sorry, we have cosine B there. If we look at the second fraction, we have cosine A there and cosine A there. So technically speaking, all we're left with is sine of A over the cosine of A plus the sine of B over the cosine of B. And by now, we would know that the sine of A over the cosine of A would give me the tangent of A plus the tangent of B. Alright? And if I quickly go back up, that is exactly what you wanted. So now that you have gotten to the proof, we can now simply say that the left hand side is equal to the right hand side. Alright, QED. And of course, this means that which has been proven. This is question B, and my task here is to prove that the tangent of x plus y minus the tangent of x is equal to the sine of y over the cosine of x multiplied by the cosine of x plus y. Now, in this particular scenario, it looks like it's a good case for me to take the left hand side. Alright, so I'm going to have a statement that says taking the left hand side. Alright, so let me rewrite the left hand side here. This is the tangent of x plus y minus the tangent of x. Alright. Now, if I look on the right hand side, I notice I say sine and cos. So ultimately, that tells me that I need to change this out. Now, we know what happens with the tangent. We can change that out to the sine of x plus y over the cosine of x plus y. And the tangent of x, of course, we can change that out to the sine of x over the cosine of x. Alright, these are two normal fractions. And just like with algebra, the approach that we take here is to simplify the fractions by finding the LCM. Now in this case, my LCM will simply be both of my denominators here, which I can write as the cosine of x plus y times the cosine of x. Alright, I will say The cosine of x plus y into all of this would simply give me the cosine of x. So I would have the cosine of x multiplied by my numerator, which is the sine of x plus y, minus, similar approach here, the cosine of x into all of this denominator is going to give me the cosine of x plus y. So I'm going to have the cosine of x plus y, and this is going to multiply my sine x. Now let's take this down some more. All right, the denominator I'm not going to trouble because it looks exactly like what I want in my answer, so I'm going to leave that alone. However, in my numerator, I could apply the use of the compound angle formula here. So to avoid any form of confusion, let me use two brackets. So I'm going to have the cosine of x, open a bracket here, minus, probably I could bring that sine x to the front. You don't have to, but I could. And I open my bracket there, and all this goes back over. Now what they did with this denominator here is that they use a commutative property and write this as a cosine of x times the cosine of x plus y. Now recall now, what is the compound angle formula for sine? So we have sine x plus y there, which is going to give me the sine of x, cosine of y, plus the sine of y times the cosine of x. What about the cosine of x plus y? That is going to give me cosine x, cosine y, minus sine x, sine y. All right, good. Now, I would want to examine this to see if there's anything I can do here. It seems that there's nothing I can do, so I'm going to have to expand these brackets. So my cosine x in front of my first bracket will multiply everything inside of the bracket. It's going to turn out to be cosine x sine x cos y plus, when I multiply cos x by the second term there, and notice the second term has sine y cos x, so if I multiply cos x by cos x right there, ultimately I'm going to end up with cos squared x. All right, so because the thing is commutative, you can write this how you want. So I could write it back as sine y cos squared x. All right, let us look at my second bracket. When sine y multiply all of that term, sorry, when sine x multiplies all of that term, I'm going to have sine x cos y, plus paying keen attention to the signs there. But when sine x multiplies sine x sine y, that becomes sine squared x sine y. And all of this goes back over my LCM, which is cos x plus y. Now let us examine the numerator very carefully, looking for anything that might look alike. And there we go, we have two like terms. So this term would take out that term. All right, what am I left with here? I'm going to have sine y cos squared x plus sine squared x sine y all over the cosine of x times the cosine of x plus y. All right, let me take this down some more. Look carefully. We're going to have to apply our algebraic skills here, because if you look inside of your numerator, you would notice that sine y is common. So I'm going to factor out a sine y. If I factor out sine y, I end up with cos squared x plus sine squared x. A lovely identity we can see there. All over cos x plus y. All right, let us take this thing down now. Now I can recall that the cosine squared of x plus the sine squared of x is equal to 1. And this is a very powerful identity right here, right? That's something that we must know. So this identity, this is going to become sine y times 1 all over cos x into the cosine of x plus y. And because 1 is a multiplicative identity, 1 multiplied by sine y will ultimately give me sine y over the cosine of x times the cosine of x plus y, which if I go back up, that is exactly what we wanted. That is what we have on the right hand side. So now I can make my concluding statement that my left hand side is equal to my right hand side, QE